All right, welcome back to Introduction to Computer Networks. This is Polly again, streaming live from NTU. And you know what? This is going to be the last live stream this semester, because next week Polly is going to be on conference travel, and the next week is the final week. All right. And yeah, hi, Ouyang. Okay, good. So let's check out what's in the announcement. As you can see, Polly has posted the videos to watch for week 15. Okay, but there might be some minor adjustments Polly needs to make after the lecture today. Okay, so essentially you guys will play back the videos from last semester's stream. So I think that's about an hour of playback. And then you will follow some of the playlists, okay, on the YouTube channel. And so playlist ch555, chapter 5.5, there's no quiz. For chapter 6.1, no quiz, but for chapter 6.2, there's one quiz. Okay, for chapter 6.3, two quizzes. All right. So if you play back last semester's stream, you will see Polly talking about the quizzes, so you can just follow, okay, pretending that you are attending lectures. Now for these, there'll be additional videos explaining what the quizzes are for, okay, and that's inserted in between the video segments. So after you follow the playlist one video at a time, you should run into a quiz, okay, or a couple quizzes in the middle of a playlist. And after you understand what the quizzes are, then you come to the Discord channel and work on the quizzes. So week 15 quizzes are all posted already. Okay, so if you want to start early, for example, this week, you can always start early. So that's the announcement. All right, so in a way that you are prepared already for week 15. And let's see, who else are also here? I think Maria, Miguel. Okay, so Miguel probably say good afternoon when it's morning, right? Kaze and Nutrio. Yeah, I think I finally pronounced your ID right. Okay, Nicholas. And then Tingy. Good, so let's check out the topics today. Yeah, at the end of yesterday, I said that there's a very interesting property with the distance vector routing. That is, good news, travel fast, but bad news, travel slow. Okay, so much of the first hour today is going to be about how the bad news travels slow. No worries, let's start from the first video, that is to illustrate how good news can converge really fast. This video about 2.5 minutes. So one very interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converge really fast. But if it's bad news, meaning if a route suddenly go bad, okay, it will take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. Okay, so let me describe the first case, the good news travel fast case. So recall. Okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Bellman forward. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1. So at time 0, y is going to detect the link cost change and update its DV and inform the neighbors here and here. So next point in time, z here, is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay, therefore z is going to update the shortest distance to what? 1 plus the cost from going from y to x, which is 1 now. That is 2, which is better. Okay, so z is going to update its own DB and send it out to the neighbors. And y is going to receive z's update. Okay? Yeah, z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I don't have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same. Okay, no more message being sent out. Okay, back to z. Network converges. Everyone goes to the steady state. The second case is the bad news travels slow. So you see from the scenario, the link cost, instead of dropping to 1, now goes up to 60. Super bad news. Of course, x and y here would detect there is a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travels slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay. All right. So in short, the intuition is this: if you recall Bellman-4 equation, right? What it does is to select the better path. So if it's good news, such a good news will be selected and propagated really fast next, right? But bad news, if there's a link cost change that is going bad, then Bellman-4 will not select it, and so such a bad news will stay in the network for a while. Okay, so that's the idea. So to illustrate bad news travels slow, we're going to go through a series of quizzes starting from quiz 45. Okay. So in quiz 45, the scenario is changed this way. So link cost between x, y is changed from 4 to 60. So bad news. So what we will do here is Polly showing how she derives x table right after the change from 4 to 60. And we call that moment at right after the change T0. After Polly showing you how x's table is derived, then you'll be asked to work on y's table right after the change. So it's the equivalent of Polly solving this, and later you solve for the table of y. So let me play the video solving what is x's table at t0. Yeah, quiz 35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that will be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through the first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy came from no y earlier. So dy y, then it's 0. And then, for the second neighbor, z. What is z's perspective, the shortest distance to y? That will be what? dz, to y. So dz to y. And that is in, distance vector of z came from no z earlier. Z to y, it says 1. So we put 1 here. Okay. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z. All right, so yeah, we managed to derive x table at t0, which is 0, 51, 50. Now you derive y's table, get t0. So what do? We go to the score. W14 quiz 45 channel, all right? So similarly to quiz 44, the whole point is for you to exercise distance vector, especially the Bellman-4 equation computation. So we will not be taking the fast responder for bonus. The bonus will go to the solutions that are the most detailed in derivation. And guys, for this one, yeah, you might need some time to get the Bellman-4 equation refreshed. So you guys have 8 minutes. Okay, so do exercise and calculate y's table according to what y knows. Okay, 8 minutes. Oh, and by the way, yeah, you can actually write on the notebook and take a photo and upload that if that's easier for you. All right. Hey guys, all really nice effort, but not quite right, guys. Not quite right. Okay, so Sylvain, first of all, I see that you've changed the formulation. Yeah, so this time the formulation is correct. Okay, but the values you plug in here are not quite. Ting Yi, I think your case is similar to Team 2. Team 4, yeah, your thinking is the same as Team 5 and Team 2. But 2, 5, 6, 4, you guys are not thinking distance vector. Maria's thinking is more distance vector. So I see, okay, so I hope I can expand this a little bit bigger. So dyx, yx, and xx, okay, yz, and then zx. So this formulation is correct, and the values you plug in here is also all right. But for dyz is a little bit strange. Yx, xz, yz, zz. But dxz, oh, you know what? Yeah, you're right. Okay. Yeah, Team 13 is perfect. Okay, Maria, congratulations. Oh, wow. Gold medal here. All right, and a little bit of bubble tea also. Let's see, Team 14. Yeah, you're thinking the same as Team 4, 5, and 1. Hey, guys, I'm prepared. Yeah, some of you get a little bit confused, okay? But I do see some of the teams getting it right. Okay, Team 12 is correct as well. Team 3 is correct as well. Okay. So A6, 14, and the first 3 not quite true, not quite right. You know what? No worries. Observe how Polly derives y's table at t0. dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful, and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through 2 neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6, 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first. And then z says, I know a way to x, which is, yeah, the O impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change. No y, okay, have not yet received the new dz, new dx yet. So y is going to be using the old dz and old dx. Therefore, you see, okay, the old dz is telling y the shortest distance from z to x is 5 here. Okay. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x. All right, tricky, isn't it? Yeah, because in distance vector routing, it's a computation based on local information. You don't see the graph. You only see information from the neighbors previously, okay? From local and previously. Okay, so temporally and spatially both limited. All right. So Miguel, that was a great question. Yeah. So you guys are taking d something to something as if you see the graph and what is the best d something something, but no, you have to take it from the table that's on the local distance vector table. Okay. So now let's go on. All right. That's just the first iteration right after the change. Now let's try to develop Z's table. So Z's table here at T1. Okay, that's after the first iteration. So we just finished deriving X and Y at T0. Now let's develop Z's table at T1. Okay, remember, you are now router Z. And you will do the computation solely based on the information locally here at this moment in time. Okay, let's try it again. So let's go to channel W14, quiz 46. All right, so the question is already here. You guys are given, how about 6 minutes? Okay, so now you've exercised Spellman 4 equation already. 6 minutes to derive what is dz, okay? So let's go ahead and start. right, guys. Yes. Yeah, so Zhenyu was not quite right earlier, but yeah. So I think Jin Tao here is the first one who's got it all right. Okay, but Maria is also. Okay, very good. Where's my gold medal? Yeah, right here. Okay, Sylvain also get it right the first time. Okay, so I see that Miguel, you are also correct. So in fact, I think all are correct now. All right. Yeah, so hey, you get the idea a little better this time, isn't it? Yeah. So, but let me show you the video, Polly deriving Z's table at T1. Okay, so this one is very short. You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, yeah, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2, right? And at T1, Z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-4 equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 wings. And therefore, we update dz to 7, 1. Okay. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5 and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finish calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Okay. And that's quiz 47. So how about calculating y's table at T2, which is exactly this. Yeah, calculating y's table at T2. All right, so let's go to channel 14, quiz 47. Similarly, you guys get, how about just 5 minutes time this time? Okay, I think you guys are all getting it. So let's see which one calculates faster. All right, so this time I'm taking the fast responder. In 5 minutes. Hey guys, first responder with the detailed derivation, please. Sorry, Justin, expand your solution. So Polly is also calculating it. Yeah. Okay, I guess you guys are picking things up really fast. Okay, so Sylvain need to edit once. Yeah. You know what? I'll just take everyone for bonus. So nice try, Justin. Very good. Miguel here. Very good. Yeah, so hey, how about Polly playing the video deriving Y's table at T2 and explains how come such a bad news takes 44 iterations to converge. Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x, through neighbor x, neighbor z, link cost 60, link cost 1, link cost 60, link cost 1, the xx 0, the zx, look up the table, z's x 7, 7 here. So wow, we get a. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1, but you see y here actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only $7 to go to x. And this is going to go on, in fact, because y here is going to announce dy also, to all the neighbors. And z is going to recalculate the dz. And guess what? The next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cause to x. So until, in dz, the value becomes 50, 1, 0. Okay, and how many iterations would that be? Yeah, came all the way from 7 to 50, that will be 43 iteration. Okay, and including the initial iteration, that will be what? 44 iteration. Okay, until Okay, z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true. Yeah, so including the iteration right after the change, total 44 iterations. Okay, so you see that 6, 1, 7, 1, 8, 1, that thing will go on until 61. Actually, no, 51. So that is bad news, Trevor. So I think it's very clear, right? This property shows in distance vector now. Now there's a solution for this bad news traversal issue. It's called the Poisson reverse, right? So this video first explains why there's this property bad news traversal, and then give the idea of Poisson reverse. The problem here is, okay, right after the link cost change, when y is trying to recompute, okay, the best route to x to z, okay, particularly to x. Bellman-Ford algorithm says y needs to try, right, calculating the total cost through neighbor x, neighbor z. Through neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, okay, just to get from y to x. So together, total cost 60. Okay, not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. Okay, so y is going to insist. Why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So Z is going to send the packet back to Y. And Y is going to send it back to Z. Z is going to send it back to Y. So this packet here is going to loop for a while, okay, until Y discover, okay, the real shortest path to x. So Z here, okay, being still under the impression that the best route is the one before the link change, okay, needs to know about the link change. Poisson reverse is working this way. This is to help, okay, preventing bad news traversal. In Poisson reverse, y and x, okay, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite. Okay, that way it prevents, okay, y selecting z, okay, as the shortest distance to x. All right, so that's exercise Poisson reverse in an example. Well, it's the same example we've been using for quiz 45 to 47. Let's use the same example to illustrate how Poisson reverse works. So taking one step back before we have the link cost change. Now z here will discover a shortest path to x this way, z, y, x. So shortest distance from z to x is 5, and the next hop router is y. Now, link xy here, the cost changes from 4 to 60. X, y, these two routers being connected to the link will be able to discover the link cost change, but z here being farther away couldn't. As a result, z will be telling y, hey, this is the shortest distance from me to x. And that's why in quiz 35, when we're calculating the shortest distance from y to x, we ended up having this, right? Because z is a neighbor of y, link cost is only 1, and y is being told by z, 5 is the shortest distance to x, therefore we do 1 plus 5, and we ended up having 6 here, okay, a funny value for the shortest distance from y to x, which we see from the network after link cost change, there's no way this is the right value. So to avoid, okay, having confusion such as this, we should stop, okay, z from keep telling y this is the shortest distance. So z tells y instead, okay, the distance to x is not 5, instead being infinite. Okay. And that is what you're seeing here. Distance from z to x at y's table now being infinite. And how do we achieve that? It's not that hard.
So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. Okay. If this node here discover there's a route coming from the neighbor and using itself as the next hop. Okay. So if Y here discover in one of the neighbor, okay, and this neighbor is using itself, okay, as the next hop to a destination. Okay. Set this entry here in Y's table to infinite. With now dzx being changed to infinite, the way we calculate dy in iteration t0 will be different. Okay, so dyx particularly is the entry with different value. It was previously 6. Okay, but now let's see how it's going to look like from y to x. Okay, there are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx. dxx, dzx. Set up table, xx 0, zx infinite. So 0 here, infinite here. Comparing the two, yeah, 60 better. Okay, therefore, shortest distance from y to x is now, yeah, the direct link xy. And then the next point in time in T1, z here is going to receive the distance vector from x and y, and this time dyx is 60. That's going to change, yeah, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1, 50 and 1. dxx and dyx, dxx, dyx, so xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here, from z to x, yeah, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. Okay, and so y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes, 60 and 1 are the link cost. dxx 0, dzx, zx, entry value being 50. So 51 compared to 60, 51 wings. So to go from y to x, now the shortest distance is, yeah, this path. And in fact, at this point in time, so let's update the distance vector for y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
All right, so Poisson reverse addresses the bad news travel slow issue. All right. Well, you know what? It's 11:10, perfect timing to take a break. After we come back, we'll summarize the 2 routing algorithms we introduced in chapter 5.2. So, break. right, so it's 11:20, so let's come back to the lectures. So this is the summary video, about 5 minutes.
Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. dv is the distance vector. Let's compare the message complexity first. If you recall, in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links. There are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost N E. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. So overall, the cost can go as high as N cube. So link state message complexity, not good at all. Distance vector, on the other hand, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. So in terms of message complexity, dv is slightly better. Now, the second metric, the speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being n squared. There's some optimizations one can apply that takes you to n log n time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state, very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase the router is malfunctioning, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short link cost to a particular neighbor, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DV and then pass the incorrect information further. Each node's table is going to be used by the other. Each node's distance vector is going to be used by others. This error is going to propagate out throughout the network, and it might take a long time for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, link state here is still winning by a head, by a neck.
Okay, now, guys, if I would like to take a poll between link state and distance vector, which one would you prefer? Okay, feel free to pick one based on your intuition. All right, LS or DV, which one you prefer? Type it up on the chat, please. Okay, I see Isa. Very enthusiastic LS. And Sophia prefers DV. All right. Let's see, who else? Hey, August, that's a sophisticated answer. LS for intra and DV for inter. Okay. Hey guys, you guys don't know what's intra A is, what's inter A is yet. Okay, so yeah, I guess August has some experience in the industry already, so yeah, he knows the best which one to use. But I see Zhenyu prefers LS, Miguel DV, Jeremy prefers LS, Sylvain also LS, LS, okay. LS if there is enough memory. Okay. A little bit more consideration from Justin. Hey, okay, interesting. I have to say that after the summary video, this class preference is actually different from last semester's class. Hey, Sophia, you're the only. Oh, okay, Miguel also. Hey, Sophia, Miguel, team number 3. Just prefer distance vector better than link state. But all the other guys, LS. And August, you know the two of them very well, so I'll just not count yours. All right, good. Hey guys, I'm gonna take the poll. I'm gonna take the poll again after I introduce this notion called autonomous system. Okay. So this next video is to talk about this. If you recall back in chapter 1, the internet is a network of networks. Okay, so it's a network at the higher level. And each node in this high-level network is a network. So each of these smaller network at the lower layer, okay, is a local area network. Okay? And such a local area network typically is under the same management, okay, under the same administration. Okay? So that low-level network is called a autonomous system, or AS. Okay? So this introduction introduces first, if we just simply use LS or distance vector to do internet routing, what the headache is, and why it's necessary to break the internet from a flat network of machines to a network of networks. So this video, a little bit long, okay, almost 6 minutes.
Next, we'll be talking about 2 routing protocols that are actually running on the internet. First is called the OSPF, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, BGP, is then based on the other routing principle, the distance vector routing. Well, to be exact, BGP is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, okay, OSPF is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, okay, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. Okay? So until now, the way we're introducing these routing algorithms is actually very idealized. Okay? Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, okay, there's going to be how many? Yeah, these many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, okay, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not gonna work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, okay, you don't wanna go there. Okay, so even if we use a more scalable routing algorithm, distance vector, okay, consider it working on the internet, not gonna scale. Okay, we cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers nearby belonging to another organization, another system. Now each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here, they will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, 1 or 2 routers and make them the delegate routers. These delegate routers, okay, at the higher level, will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, the backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see 2 levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems.
Okay, so Polly is gonna take the poll again. If now you are a network administrator for a AS, which routing would you use? Link state or distance vector? Okay, now type your choice on the chat. Let's see. Okay, DV still for Sophia. DV? for Sylvain? I guess the others are still debating, right? If I am a mean for an AS, Isa also, hey, DV. Okay, so Kaze offered the explanation. DV because the memory cost is smaller than link state. Okay. All right. Yeah, so if you are a network admin, I suppose either way is fine, isn't it? So again, this is still a little bit more the preferences. Yeah, but for this time, interesting. Okay. Yeah, I see that in Kaze's case, the memory efficiency it does matter. Hey, I guess this has something to do with August typing this. Okay, the current internet full table, there's a million IPv4 routes, and that takes 4 GB memory already. Okay, so it seems that memory consumption is a major issue. That's probably why you guys are prompt to select DB, as opposed to previously link state, isn't it? Okay, just looking at the comparison. Okay, and maybe focusing more on robustness, link state seems to be easier to work with. And if you are really managing a system, you guys consider a little bit more. Okay, good. Interesting. But you know what? Yeah, that routing algorithm that you choose as a network admin will be working intra AS, within an AS. Okay. There's another routing that's running across ASs, that's inter-AS routing. At the end of the video, I said that, hey, for the whole internet, there can only be one inter-AS routing. But intra-AS, you guys get to choose distance vector or link state. Okay, so the next video explains a little bit more intra-AS routing versus inter-AS routing a little bit more.
Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border of the AS. These powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. Gateway is what? The doorway. Yeah, the routers sitting at the border of these AS connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, of its own AS, and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, running in the backbone of the internet, is called the inter-AS routing. Okay, so that is the routing protocol that's running across the gateway routers. So this is the routing, working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have 3 ASs, 1 here, 2 here, and 3 here. You see individual routers interconnected within one AS. Okay, so there are 3 here for AS2 and 3 more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, but you see 1B and 1C, both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. Okay. And inter-AS routing is running in between. Okay. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have two levels of routing running on the internet. Okay. Now, let me show you an example here. Okay. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, okay, not within the region, right? You need intra-AS routing to find the gateway router. And you also need the gateway router, okay, to find, hey, where's the destination gateway router? All right, so you do need inter-AS routing algorithm telling, okay, each node where to pass data further. Just like you need intra-AS routing there telling you, okay, how to reach another router within the AS. Forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries, okay, for destinations within the AS, okay, within AS. And inter-AS, okay, determines entry for the external destinations. Okay. To be precise, the inter-AS determines which gateway, okay, which router here you should be passing the data to. Okay. But intra-AS will also be telling 1D here, okay, to go to that particular gateway router, what is the right way? So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS.
All right, so one more example to illustrate better the interplay of intra and inter-AS routing.
To make sure the interplay of the intra-AS and inter-AS routing is more clear, let's take a step back. Okay. Look at AS1 here. 1A, 1B, 1C, and 1D. Okay, so these routers within AS would run the intra-AS routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AS routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A obviously a gateway router for AS3, but you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, 2B, 2C all have links to outside to other ASs, so they are also gateway routers. So these gateway routers at the higher level will be running the inter-AS routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there is another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. With those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. they do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS? And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS router.
All right, so you see there, inter-AS routers, the gateway router, not only do the inter-AS route computation, they also propagate whatever the routes they come up with internally to all the routers within the AS. All right, next, let's focus on the intra-AS routing protocols existing on the internet. All right, so the first video talks about the options we have.
The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within an AS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within an AS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution in the 1980s, late 80s. And it's based on this principle, distance vector routing. Okay. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. But this other one, OSPF, short for Open Shortest Path First Routing Protocol, this one on the other hand is very popular. Okay. So open here stands for open source. Okay. RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, in SDN, pretty much are doing what? Generalized forwarding, and allowing the flow table being installed, and that's pretty much all. There's no need of running routing algorithms on individual routers. So Starting from 2016, Cisco stopped maintaining iDrip because there's really no need, very little need of doing routings inside the router.
Yeah, so 3 options. Okay, but the first option, RIP, is really old, and I'm not sure if it's still maintained. The last one is for sure eDrip. It's proprietary, but it's for sure not maintained. So in the end, guys, I ask you guys, in case you are the network admin, which routing algorithm you will use. You guys all pick DV, but in reality, in the industry, LS is used more for 2 reasons. One is that, hey, we know LS is more memory consuming, but you see, it's only working for a local area network, right? Only within an AS. It might still be okay. It's not like you have all the routes of the internet. Second reason is this, okay, the same reasons you guys choose LS to begin with, okay, after the summary of the 2 routing algorithms. It's a lot easier to manage. So link state actually eventually stands out for intra-AS routing. So OSPF is this link state routing that's used commonly. ISIS, although very old, is still used and quite a bit. The 2 of them, I would say that in terms of the design, a little isomorphic. Okay, they are essentially the same. But of course, the detailed definitions are somewhat different. And OSPF, you thought, oh, the memory consumption will be high. But in the next video, Polly will introduce OSPF more, and I will introduce how you can make OSPF or ISIS more scalable. Okay, I think that's why in one of the lectures earlier, August, who has experience in the industry, saying that he's been using ISIS and no problem at all, and it seems to scale well for intra-AS routing. All right, so hey, I only use those for router discovery. If anything, interesting. Okay, else happen BGP including internal routing. I see. Yeah. Okay, so so I guess August was not using ISIS, but in practice, many admins mix the use of OSPF and ISIS. And some prefer using just ISIS, and some prefer using just OSPF. So you will see a hierarchical OSPF you can implement as well to make the memory consumption a little bit more scalable. So this is the next video, a little bit long, 6.5 minutes. The whole lesson about a 6-minute crash lesson about OSPF.
Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, yeah, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in OSPF message. These OSPF messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. Okay, there's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cause of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. one can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3. Okay, inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay? The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at the higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.
Yeah, so that was intra-AS routing and OSPF. Now the inter-AS routing, and there's only one, so essentially BGP, the routing protocol that's running inter-AS these days. So the first video is a overview of BGP.
Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the BGP. Now, this is also the routing protocol that runs on all these gateway routers, okay, that are higher in the internet routing hierarchy. OSPF, DRIP, eDRIP, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS what is the entire AS level path, inter-AS level path. So that inter-AS level path will contain all the intermediate ASs, okay, along the way from the source AS to the destination AS. So what's nice about keeping track of the entire AS path is this. The source AS knows by default what is the next hop AS. And by counting the number of ASs along the way, you get a rough sense of the path cost as well. But the downside of tracking the entire path is that the memory requirement is higher. But this is okay, right, at the inter-AS level because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So path vector is exactly what BGP, this one and only inter-AS routing, is based on. First line, BGP stands for Border Gateway Protocol. And once again, it is the one and only inter-AS routing protocol that's holding the internet backbone together. To be more precise, it allows each AS the following. First, it allows the gateway router there for the AS to receive subnet reachability information from the neighboring ASs. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the AS receive path vector from the neighboring AS's gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination AS. Okay? And there are many of these destination ASs, therefore, we receive the path vector, okay, from the gateway routers of the neighboring ASs. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring ASs. As a result, okay, each of these routers within the AS can calculate what is the best path for a particular destination AS. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the AS. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good AS path is selected for a destination AS, the border router there, okay, then can append, okay, the AS's AS number to the AS path derived, and then further propagate this to the neighboring ASs. Okay, so that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. And of course, okay, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. it will announce itself existence to the rest of the internet.
All right, so the last video today, or the last video in a live stream this semester, is going to be just a little bit more about the reachability information, the path vector, and then there's going to be an illustration with an example.
One last point to make is just this: the reachability information, aka the path vector, when they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we establish the exterior BGP connections to allow path vectors travel across borders from one AS to another. Now for path vector, that is supposed to be sent internally to all the internal routers, then belongs to the IBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs. Yeah, there are exterior BGP connections to outside, exterior BGP connections to outside. So eBGP, in red color. But in addition to that, 2A and 2C both need to send path vectors internally. Okay, so you see they went through the IBGP connections. All right, so IBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. Yeah, they run both the eBGP part of the protocol as well as the IBGP part of the big BGP protocol. Those BGP connections are often referred to as the BGP sessions. So these routers will exchange messages over semi-permanent connections. Yeah, the reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP, BGP is a routing protocol, right? These messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the path vector? So these messages that we're exchanging between the BGP routers, the path vector is being sent reliably or not? Yeah, to push it a bit further, what about using TLS, okay, the secure version of TCP? And if we use TLS, these BGP messages, these path vectors, will look more like an application level message. You think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. Yeah, the path to all sorts of destination networks, the path to all sorts of destination ASs. In fact, altogether, we just call it the path vector. Okay. So BGP, again, a path vector protocol. And let me give you an example here. So let's say in AS3, okay, there is a prefix X. And this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, okay, advertise it to outside of AS3. So 3A here, okay, will need to announce, okay, its existence and pending its own AS number, so AS3 here. So this will be the AS path, okay, being advertised. This will be the AS path being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, okay, will receive the AS path, AS3, X. So AS3's gateway router 3A will advertise the path to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X. Right?
Yeah, so that was BGP and how these path vectors are passed around and accumulate and propagated further. Sounds like what? Distance vector. Yeah. You know what, guys? It's 11:09. This is all the time we have. Okay. So the rest of the videos, I'm gonna update the links that I posted in the week 14 ep24 announcement. I will also post a message for week 15 so that it's clear exactly what you guys will need to follow next week. All right. With that said, I say goodbye for today and goodbye for all the live streams this semester. Okay, bye.